Hello, listeners. Welcome back to my channel. All right, so this is the last lecture for Module 3. And in this series of videos, we start with the molecular interpretation of entropy. And things can get a little bit abstract because we'll try to relate entropy with probability. Then we will look at the third law of thermodynamics. And lastly, we'll try to discuss standard molar entropies and some related calculations. All right, so to start, let's try to consider the mixing of two ideal gases at constant pressure and temperature as shown in this slide. Now, these gases are placed on separate bulbs that are joined by a stopcock. You can expect that when the stopcock is open, the gases will mix until each is evenly distributed throughout the entire apparatus. Now, throughout this mixing process, the volume, total pressure, and temperature remains constant. Since the gases are ideal, no intermolecular forces exist and neither the internal energy nor the enthalpy of the system is affected. Now, this process occurs spontaneously and represents an increase in the entropy of the system. So, this means that entropy is a non-zero in this process. Now, what else is expected to increase aside from entropy? So we can actually see here that probability is also maximized. Considering the example, the final state is more random and hence more probable than the initial state. It will be surprising and even impossible if the reverse were to be observed. That is, if the gaseous mixture separates into two pure gases, each occupying separate bulbs. Now, if we assume that the equilibrium state of the gas, which is the complete mixing, is a state of highest probability, then it is understandable why the gaseous mixture never separates back to their pure gases. We can say that the gases achieves its most probable state by occupying as much volume as it is available to it. All right, so based from that example, we could say that for an isolated system, processes tend to proceed in directions that maximizes its probability up until a state with maximum probability, and this is known as the equilibrium state. All right, so let's try to mathematically relate probability with entropy. So this means we have to express probability as a function of entropy. To do this, let's consider a system which is divided into two parts as shown here. System part 1 has entropy 1 and probability 1, and system part 2 has entropy 2 and probability 2. Now, the total entropy will be the sum of the entropy of its parts. This relates to the fact that entropy is an extensive property. Now, to combine the probability of part 1 and 2, we do this by multiplication. So the total probability of the system is a probability of part 1 times the probability of part 2. We can then express this as S as a function of probability 1 and probability 2 is equal to the S of probability 1 plus S of probability 2. Now, what function gives us this type of relationship? So this function should remind you of the property of logarithms. We could write this as S is equal to K ln omega. We can write this first term as K, which is a constant, ln omega 1 plus K ln omega 2. Using the property of logarithms, we can write this as K ln omega 1 times omega 2. Based from this definition, this can be written as S of omega 1 times omega 2, which is what we want to get. Basically, this is the Ludwig Boltzmann definition of entropy, and this ultimately relates entropy with probability. It is clear from this equation that entropy depends on the logarithm of the probability of the state. So in this equation, omega refers to the microstates, which is the ways of distributing the particles. In some textbooks, this is symbolized with the capital letter W. Now, the K here refers to the Boltzmann constant, which is simply the gas constant divided by the Avogadro's number. Now, take note that the unit is consistent with the unit of entropy. This equation tells us that we can relate entropy as a measure of probability. Oftentimes, entropy is related to chaos or disorder. Now, a better way to look at entropy is a distribution of energy. Now, just a bit of information, this equation is actually engraved in the tombstone of Boltzmann. We can also state the Ludwig Boltzmann definition of entropy as for an isolated system, the energy is conserved, which is our first law of thermodynamics. And it is the distribution of energy which is related to the entropy that determines the direction of spontaneity. So the second part of the statement is the second law of thermodynamics, and we can use entropy as a basis to tell us in which direction of processes occurs. All right, so let's try to look at some more important implications. So we know that entropy is related to the distribution of energy. So what happens if we start removing energy from our system as shown here? We could do this by heat flow out of the system. Now recall that heat flow is a type of energy transfer that involves the random motion of particles of the system. So if we have heat flow out of the system, we tend to decrease the random molecular motion and a corresponding decrease in temperature. Upon decreasing the temperature, we also decrease the entropy. And since it is related to the probability or the number of microstates, decreasing the entropy also decreases the number of microstates. Now, what will happen if we continuously remove heat out of the system? What will be the lowest limit of possible microstates? The limit for the lowest possible value of a microstate is 1, as there's only one possible way to distribute our energy or arrange our particles in the system. So based from our definition of entropy, what happens when omega is equal to 1? So using this equation, entropy is equal to 0. Now we can represent all of this in terms of limits, and this will lead us to the third law of thermodynamics. Alright, so in 1913, Max Planck suggested that the value of absolute entropy is 0 for every pure and perfectly crystalline substances, and later this was known as the third law of thermodynamics. Now, in terms of limits, this equation tells us that if we remove heat from our system and decrease the temperature all the way to 0 Kelvin, our absolute entropy becomes 0. Now, take note that this is only true for a perfectly crystalline material. The third law of thermodynamics establishes a theoretical limit to the possible temperature as well as the possible value of entropy. However, the absolute 0 is unattainable, so this is just a theoretical construct. The importance of the third law is that it establishes the conditions at which entropy is defined as 0. For convenience, these values of entropy at absolute 0 temperatures is taken as 0. This will allow us to determine the absolute values of entropies for our different systems. In other words, this will allow us to determine the different absolute values of entropies for different compounds. Alright, so let's define what is standard molar entropy. Now, the standard or the absolute entropy of any substance refers to the entropy change for the following process involving 1 mole of the substance. So the initial state is a perfect crystal 0 Kelvin and 1 bar pressure. Now, the final state is the substance at 298 Kelvin, and if it is a gaseous substance, then we assume that it behaves ideally. Now, imagine if you have a perfect crystal at 0 Kelvin and 1 bar pressure. Now, you heat the crystal at constant pressure and take it all the way up to 298 Kelvin. Then, imagine that the substance is a gas at that temperature and it behaves ideally. Now, the change in the entropy for the process is called the absolute entropy of the substance and is given by this equation. Delta S is equal to the entropy at 298 Kelvin minus the entropy at 0 Kelvin. Based from the third law of thermodynamics, we know that the entropy at 0 Kelvin would be taken as 0. So the delta S for the process would just be called the standard entropy or the absolute entropy of the substance at 298 Kelvin. Alright, so we have a table here that shows the standard molar entrophies of some selected substances. Now take note that unlike standard enthalpy change, the standard entropy of elements is not equal to 0. Alright, so how do we experimentally measure absolute entropy? In order to do this, we have to measure the heat capacity versus temperature. These are the important aspects on how we can measure the standard molar entrophies of the substance. First, we have to measure the heat capacity to a very low temperature that we can achieve in the laboratory. Then, once we get to the lowest value, we can extrapolate the Cp to the absolute zero using the Debye-P3 law, which I will discuss in a while. The next thing to do is to integrate the Cp over T from 0 to 298 Kelvin, and the delta S is simply the integral of Cp over T dt. However, along the way, as you are heating your substance from 0 Kelvin to 298 Kelvin, there will be phase transitions. Delta S for all those transitions will be the delta H divided by the temperature at that transition. Alright, so before we look into the processes individually, let us discuss an example of a phase transition. One of the phase transitions of interest is the entropy change when liquid is converted into vapor, or the entropy change of vaporization. So what is the entropy change when a liquid is changed to vapor? The entropy change is just equal to the heat change in reversible processes divided by the temperature. Now, at the boiling point, the liquid is in equilibrium in vapor, but as the temperature is equal to Pb. This means that the process is actually reversible, and the heat required to convert the liquid to vapor is defined as the heat of vaporization. Ultimately, we can calculate the entropy change as delta S is equal to delta H divided by Pb. Now, Trouton found out that the entropy of vaporization, that is delta H over Tb, is approximately equal to 85 joules per Kelvin per mole. However, some deviations were observed for substances that exhibit strong intermolecular forces, such as hydrogen bonding, and these are evident for water, alcohols, and amines. Now, using this value for the entropy change in vaporization, we can easily approximate the enthalpy of vaporization or the boiling point of the substance. Let's try to look at this example. Predict the molar enthalpy of vaporization of liquid bromine at 59.2 degrees Celsius. Alright, so we know that there is no hydrogen bonding in liquid bromine, and bromine is a heavy molecule. That is, it's unlikely to display any unusual behavior in the gas phase. So it's safe to use the Trouton's rule. Now, to predict the standard molar enthalpy of vaporization of bromine, given that it boils at 59.2 degrees Celsius, we can use the Trouton's rule in the form delta H vaporization is equal to the boiling point times 85 joules per Kelvin per mole. Now, substitution of the data will give us an answer of positive 28 kilojoules per mole. Okay, so how do we exactly calculate the standard molar entropy? Let us use the definition of entropy as shown in this equation. Again, for our standard molar entropy, we are calculating the entropy at standard conditions, which is 1 bar. We have a constant pressure condition, so we can rewrite this as dQp over P. The S naught is just NCP dt divided by temperature. Then we have to integrate from the initial state at entropy of 0 Kelvin all the way up to the entropy of temperature of interest. Upon integration, this will give us delta S, and When expanded, this will be the entropy at T minus the entropy at 0 Kelvin, which is just equal to the integral of NCP dt over T. However, third law defines the entropy at 0 Kelvin is equal to 0. So ultimately, we are calculating our initial state at 0 Kelvin to the temperature of interest is just equivalent to the entropy at the temperature of interest. Again, as we have said earlier, we have to account the different types of heat capacities and phase changes that a substance undergoes from 0 Kelvin to the temperature of interest. Alright, so this shows us the different variations of Cp as the temperature increases from 0 Kelvin to the temperature of interest. So we'll go through this in each region in succeeding slides. Alright, so we start at 0 Kelvin, and for many substances, it is very difficult to determine the Cp at very low temperatures. Instead, we do some approximations. Measurements of the heat capacity are made down to a low temperature, which is frequently lies in the range from 10 to 15 Kelvin. At such low temperatures, the heat capacity of solids follow what we call as the by P cube law, where A is a constant for each substance. At these temperatures, Cp and Cv are indistinguishable, so the Debye law is used to evaluate the integral of Cp over the interval from 0 Kelvin to the lowest temperature of the measurement. So this is the first Cp that we have to account until a certain temperature Td. After this, we can now look at the data sheets for the heat capacities of solids. Alright, so this region tells us the entropy change upon increasing the temperature of the solid until the melting temperature Tm. The entropy change associated with this step is simply Cp over T dt as shown in this equation. Once we hit the melting temperature, we have to account the entropy change associated with the melting or fusion. At this region, we are transforming our solid to liquid. If we have a phase change from solid to liquid, we know that there is a corresponding increase in the entropy. So the temperature is to remain constant. So the entropy of phase transition is given by this equation, delta H fusion over the temperature of fusion. Now, moving on, so once we have converted our solid to liquid, we can start heating up the liquid up until the boiling point Tb. The entropy change associated with this process is given by Cp over T dt, or as shown in this equation. At the boiling point, we have to account the entropy change associated with the vaporization process. So this occurs at constant temperature, and the entropy change is given by this equation. Once we have converted all the liquid to gas, we could now take into account the Cp of the gas in order for us to calculate the entropy change associated with the process, and the entropy change is given by this equation. Alright, so we have to consider all the entropy changes in all steps, especially if the temperature of interest that you want to determine is on the last step. To sum up all the entropys to calculate the standard entropys, this is given by the following equation. We know that the entropy at 0 Kelvin is 0, thus this is simply the sum of all entropy of all steps that we have discussed. Ultimately, the total standard entropy is given by this equation. Alright, so let's look at some calculations involving standard reaction entropys. Now, the standard reaction entropys is defined as the difference between the molar entropys of the pure separated products and the pure separated reactants. Take note that all substances are in their standard state, which is 1 bar at the specified temperature. Now, in this expression, each term is weighed appropriate stoichiometric coefficient. Now let's try to apply this equation in the following example. Calculate the standard entropy change in the following chemical reaction. So you have 1 mole of hydrogen reacts with half a mole of oxygen to give you 1 mole of water. The standard entropy is simply the difference between the absolute entrophies of the products and the reactant. Now, expanding this equation, we have delta S north reaction is equal to the absolute entropy of water minus the absolute entropy of hydrogen gas minus 1/2 the absolute entropy of oxygen gas. Now, substituting these values, which we have taken from data tables, and evaluating this equation, this will give us negative 163.4 joules per Kelvin per mole. All right, so we have to remember that standard entrophies are likely to be positive if there is a net formation of gas in the reaction, and they will be negative if there is a net consumption of a gas. Alright, so the last topic for this video is the temperature dependence of entropy. So we can actually calculate the variation of temperature for our standard molar entrophies of reactions. Now, this is similar to the Kirchhoff's rule that we've discussed previously. Actually, entropy has an equivalent version of the Kirchhoff's rule. Now, we are interested in determining the variation of temperature of this equation, and we can do this if we take the derivative of the terms in this equation with respect to temperature at constant pressure. Now, rewriting this, we get the following equation. Differentiating this equation with respect to temperature at constant pressure, we have this following expression. We can define this term as ds naught is equal to Cp over T dt. Now, we can rearrange this equation by transferring the differential dt on the other side to get the following expression. We can now make suitable substitutions in our formula to give us the following expression. The terms here are essentially equal to delta Cp, therefore this equation becomes the following expression. Rearranging this equation, we get the differential of delta S naught is equal to the delta Cp over T dt. Now, integrating between the reference temperature, let's say T sub O, to any temperature of interest, let's say T, we obtain the following expression. Now, this equation is applicable to any chemical reaction as long as none of the reactants or products undergoes a phase change in the temperature interval between T sub O to the temperature of interest, which is T. Okay, so the last thing we have to look at here is that if the Cp is independent of the temperature, so we could easily pull it out of the integral and the equation simply becomes this one. Alright, so this is the last topic for this video, and in the next video we will look at the criteria for spontaneity and we will try to derive two more state functions that we can use to tell us the spontaneity of chemical processes.